Okay, so hello everybody. Today we have an additional lecture on chapter 3. So we have to finish what we have not finished last time. And I have to say that last time I made a typo on my slides, and this caused a problem, a mistake in the proof. So I'm talking about theorem 325, which we have discussed last time. So if so, so the statement was as follows. So if X with the scalar product is the scalar product space, inner product space, X0 a closed subspace of X, then its orthogonal complement is a closed subspace of X, and we have this representation. In particular, for each X, for each element in X, there exists a unique element in X0, such that we have this. And moreover, due to the lemma, we have this. And this unique x0 is called the orthogonal projection of x onto x0. So what was the problem? So it was in this part of the proof. So wait a minute. So I have specified the following. Since x0 is closed, there exists x0 such that the Cauchy sequence converges. So this is true only if this x0 is complete. So we have already discussed before the difference between completeness and closeness. Any Cauchy sequence has a limit in the case when everything happens in a complete space. If a space is just closed, it is closed in some ambient space, and so the closed subspace contains all its limit points, which are available in this ambient space. So probably they are not all limits of Cauchy sequences. That is, we should be careful here. So in order everything works okay here, we should assume one of two things. So one possibility, if X is complete, then, of course, x0 as a closed subspace of X is also complete. Or second possibility, X is just an inner product space, not Hilbert space. It's just an inner product space. Probably let me be even more rigorous. So if X is a complete inner product space, then x0 is also complete. And second option, if X is just an inner product space, then we should require that x0 not only closed but complete. That is, we should modify the statement of the theorem in one of these two ways in order to keep the proof to be totally correct. So I suggest we correct it in this way. So we consider Hilbert space, the complete inner product space, and then everything is okay with the proof of the statement is correct. Okay, so this is a remark concerning the last lecture. So I have this modification on the slides of last lecture. So I will send you the updated version, the corrected version. And now we go to lecture 7. And so now we have this theorem 3.25 with Hilbert space X. And once again, so last time we have proved this part. From this follows all the rest. But I would like to stress that what we have is really the direct sum. So let me recall, it was remark 310 about the definition, which space is called the direct sum. So if we have a product of inner product spaces, we have several inner product spaces, then such vectors provide us with inner product, are elements of inner product space. and we have such scalar product in this inner product, in this direct sum, and this norm in this direct sum. So what has happened in our case in this statement? So we have presented that each x can be represented as x0 plus x minus x0 with these conditions. So from this we know that the norm of x squared will be, by Pythagoras theorem, will be just the norm of x0 squared plus the norm of x minus x0. That is, we map x to this couple x0 and x minus x0 as here. Yeah, so we have two inner product spaces. Actually, they are closed, and they are closed subspace of a complete space, so they are all complete. So that is x0. We have x0, it's a Hilbert space, and we have its orthogonal complement. It is again a Hilbert space. In both spaces, we have the same scalar inner product, the original one. And so just using the properties of orthogonalities, using the properties of scalar product, we see that this and this, they both take place. So these two equalities are true in our setting. That is really, our x is represented by a direct sum of these two Hilbert subspaces. Okay, are there questions concerning this or not?
No.
No. Okay, so we can go further. So we remember the statement. And now the next statement is a corollary from this theorem. So let X be a Hilbert space, X0 a closed linear subspace. Again, this linear and subspace, it's like oil is oily. So just subspace, which is by definition a linear subset. Okay, so this mapping, which X is mapped onto this, its orthogonal projection, this mapping is called orthogonal projector or orthogonal projection. This mapping, as a mapping, is linear and continuous, and we have the following inequality and the following statement that this orthogonal projection applied twice is the same as just orthogonal projection applied once. So this is what we want to show, and this is the proof, so we don't need to write anything. So we first show the linearity. So let X be element of the space X. Then for every scalar from our field, we have the following. Orthogonal projection times alpha is again an element of the same vector subspace x0. So this guy lives in x0, that's why alpha times this element lives also here. And using the properties of scalar product, we see that this guy is orthogonal to x0. Yeah, just what is written here by the properties of scalar product. Hence, this is the unique element which is orthogonal to x0, and hence this is the orthogonal projection of this element. So we have this. And hence, homogeneity of this mapping is proved. In a similar way, additivity. So we have two elements x, y, and x. So since this guy and this guy, they live in this space, which is a vector subspace, then this guy also lives here. And we see that this guy minus this sum is orthogonal to the space x0, again by the properties of scalar product. Again, from this theorem 3.25, since there exists the unique guy which makes the business, since we have this identity, this means that this guy is the orthogonal projection of this guy onto x0. So we have shown that what we have shown? We have shown that the mapping is linear. So I guess it is written. So what we have see first. Yes. So I guess it was written here. And now just we have added this sentence, which I have already pronounced. So due to the uniqueness of the orthogonal projection, we have this identity, and hence we have shown this and this. This means that this guy is linear. Okay, let us go further. Continuity. Oh no, first we show this. So we know already that x minus its orthogonal projection is orthogonal to x0. We have shown it in theorem 3.25. So now we use the Pythagorean theorem. This is just the properties of scalar product, that norm of x squared is the norm of its orthogonal projection squared plus this guy. And hence we see that since this is non-negative, we have this inequality. Okay, with squares, but also since the norms are non-negative, also without squares. So we have shown this linearity and this inequality. Okay, let us go further. So since we have already shown the linearity of this mapping, we consider this norm of such difference. This is like this due to linearity of this mapping. And now we use this inequality. We obtain that this norm is more or equal to this norm. And hence, this mapping is Lipschitz continuous with Lipschitz constant 1. Lipschitz and hence continuous. So we have shown this. It's clear?
Yes, for me it's clear.
Yes.
Okay. Next, for every x from x0, it holds that its orthogonal projection onto x0 is x itself, yeah, the closest element from this set to x. So we see that this also holds. Yeah, so if you apply twice, I don't know, should I do it? px0, then x is equal to, so this is an element which belongs already to the set, and then px0 applied to this element is just this element itself. So this is just this. And hence we have shown what is required. Okay?
Okay.
Yeah, so we have finished the proof. Proof is elementary. Now next corollary, 27. So if we have an orthonormal system in a Hilbert space X, so we consider the closed linear span of this system of vectors. It's x0. It's a closed subspace, closed subspace of X. And then the following is true. So for every element X in X, we have that this series converges. And X minus this sum is orthogonal to x0. That is, this sum is exactly nothing else but the projection of x onto x0. And this is a very nice thing. So let us prove it. So by Bessel inequality, I guess it was, I don't remember the numeration, but okay, by Bessel inequality, what do we have? We have that norm of x squared is bigger or equal to the sum of lambda And here we have scalar product x and e lambda squared. And we know that the series x e lambda converges and contains at most countably many summands. So this was discussed when we proved Bessel inequality, and from this that the series converges. It is in a similar way as we did when we discussed partial equality. That is from the convergence of this series we get that, so there at most countably many summands, and then we construct a sequence of partial sums of this series and see that this is a Cauchy sequence, and it converges in a Hilbert space because the space is complete. This we have already discussed when we discussed partial inequality. So this what we have. So again, as we have already done, then x minus sum. Okay, so let me probably call these summands, which are how to call it? That is sum of lambda x e lambda e lambda. It is something which looks like this. It's k from 1 to infinity, x e lambda k, and x e lambda is equal to 0 for e lambda which does not belong to the set of e lambda k. Then we use the continuity of scalar product. So we have that scalar product x minus sum k from 1 till n, x e lambda k, scalar product with e lambda. Let me call it. Okay, lambda j. This is equal to 0 for all j from 1 till n. And now we use the continuity of scalar product. So we tend n to infinity, and we have that x minus sum k from 1 to infinity, x e lambda k is orthogonal to all e lambda k, I don't know, e lambda j, which belongs to this set, e lambda k from 1 till infinity, k naturally. But also this stuff is orthogonal not only to those vectors, but also actually to all vectors of the system because of this identity. To E lambda, which do not belong to this system. Due to this identity. Yeah, because then here we have zeros, and then scalar product x and this E lambda is also 0 due to this. So what we see that this difference x minus this series is orthogonal to, since it is orthogonal to all E lambdas from this system, both to those subsystem and to those which do not belong to this subsystem, it follows that this guy is orthogonal to the whole subspace X0. And hence, we use this theorem by theorem 325. We know that there exists a unique element for each x. There exists a unique element which is orthogonal to x0, and this unique element is nothing else. So this unique element is nothing else but the orthogonal projection of x onto x0. So we have that projection. Orthogonal projection of x onto x0 is exactly this series. And hence we have shown what we wanted to show. Okay, this is elementary and somehow we repeat the argumentation already several times, but sometimes I think it's not bad to have the complete presentation of the argumentation. Okay, so please pay attention that if we have an orthonormal basis, then we have a span, a closed linear span of the elements of this, not basis, sorry, orthonormal system. We have a closed linear span of its elements, and then we have this. This is the connection between orthonormal systems and orthogonal projections. Okay, so may I go to the next slide?
Yes.
Okay, then one more corollary. So let we have an orthonormal system in a Hilbert space. We fix an element. So the statement is as follows. So Bessel inequality is actually nothing else but Parseval inequality. So not like this in a Bessel inequality, but equality. If and only if X belongs to the closed linear span of this family of vectors. So this is the relation between Bessel and Parseval. Okay, so let us show it. So we know that we know this. And no, we know. So let me first have this. Or better to say. So we have this identity. Now we use. I guess this was remark. Let me recall what kind of remark it was. Let me draw. Let me go back. This is lecture number 6 of the previous one. We had this remark. Yes, I guess this was this remark. Yes. And this is what we have done many times. So if we have some orthonormal system, okay, orthonormal basis, but also for system, and if we have this identity, from that we obtain the Parseval equality. So now we apply it here. So we have this identity. So this guy is equal to is the sum of this series. So we can apply Parseval equality for this identity, and we have that the sum over lambdas. And here we have x in lambda squared is just the norm squared of this guy on the right hand side. So where x0 is just the closed linear span of all E lambdas from the system. So what we can see. This identity holds for x if and only if this guy is nothing else but just norm of x. But this holds due to this identity, due to these properties of orthogonal projection, this holds if and only if x itself lives in x0. So probably let me here by Parseval equality in remark. It was remark 319.2. 319.2. So we have this, and then by corollary 326, by corollary 3.26. So this statement, let me call it statement star. I don't know the color. Statement star. So by corollary star. No. What I wanted to say. By corollary 326, by the properties, the Parseval, let me call star only this Parseval equality. By corollary, this star, if and only if and only if x belongs to x0, or better to say x is the same as its orthogonal projection on x0. That is, x belongs to x0. And this is in both directions. So if this holds, we obtain this, and vice versa is also, of course, true. Okay. So now we have a sequence of elementary statements, but we have to, nevertheless, to present the proofs. So may I go further?
Could you please explain that if X belong to the boundary of the linear span, can X be represented as a linear combination or not?
So once again, I'm not sure what you mean by boundary, but we have a not finite linear combination. So what is span? Span it's a all possible finite linear combinations of these guys. And now we take closure. Yeah. So we add all limit points for such finite linear combinations.
I see. Thank you.
Okay. So now may I go to the next slide?
Yes.
Okay. So like a finalizing remark. So what do we finally have? What properties have an orthonormal basis? So we consider just any arbitrary orthonormal system in a Hilbert space. Pay attention, Hilbert space. Then the following statements are equivalent. So the system is complete. For every x, Parseval equality holds. This property is sometimes called that the orthonormal system is closed. The third property that the orthogonal complement to the family of these vectors is just original, so zero vector. This property sometimes is called that orthonormal system is total. And the fourth property that this system is orthonormal basis. So different characterizations of an orthonormal basis in a Hilbert space. So completeness, closeness, Parseval equality for every element, and totality. Okay, proof, I would say it is obvious, but let us nevertheless write down something reasonable. So y1 is equivalent to 2. It follows by corollary 328. So once again, completeness and Parseval equality. This is exactly what we have seen here. So Parseval equality holds if and only if X lives here. That is, if the system is complete, that is, this is the whole space X, then Parseval holds for every X in X. Yeah. Agree?
Yes.
Okay, and now 1 is equivalent to 3. By definition of a complete orthonormal system. So once again, orthonormal system is complete if its closed linear span is just the whole space X. In this case, its orthogonal component, orthogonal complement is only 0. So definition of complete orthonormal system plus plus remark 324.2. It was the remark that if we have a set, its intersection with its orthogonal complement it was only possible on this 0 vector of the space. And this is exactly what we have here. Okay, sorry. This is so 1 and 3 are equivalent. So not in one direction, but in both directions. I hope it is also clear. Now 2 is equivalent to 4. So let me make each direction separately. So let us first see 4 implies 2. So 4 is orthonormal basis, then it implies Parseval. I guess we have already proved it, so by continuity of scalar inner product. So as in remark 319.2. So I just mentioned it once again today. It was here. In the setting, the Parseval inequality is true. So if we have this, then the Parseval equality is true, and we had to prove it last time. Okay, then opposite direction from 2 we get 4. So if we have Parseval, so for any x we have Parseval. Then we know that, okay, as by Bessel inequality, we know that the sum converges to x. Okay, contains at most countably many summas and converges to x, again, as in proof of this remark of 319.2. So there exists, so we have discussed that if there are some constant ck such that ck squared, so this series converges, then so the corresponding series also converge is a Cauchy sequence, and if the space is complete, there is an element x which is the limit of such a Cauchy sequence of partial sums. So we have it, but if we have this means that this system is an orthonormal basis. Because each x we can represent as a limit of such sums. Again, by definition of orthonormal basis. Okay, that's it. So please pay attention that we are in the Hilbert space, but we do not assume that this is a separable Hilbert space. So we don't know how big this family is. So if it is countable or not, with this we don't know. But in any case, these are four equivalent characterizations or requirements on an orthonormal system, which guarantee that the system is an orthonormal basis. Okay, so this is the general picture. Now we are, I guess, in a simpler situation. So may I go further?
I think yes.
Yes. Okay, so now you consider special case. Oh, no, okay. So one more remark. So in general, every orthonormal system is an orthonormal basis in the subspace, which is just a closed linear span of all vectors of the system. Okay, it's, I hope, an obvious statement. Okay, now we consider special case, separable inner product space. So now, due to separability, we don't need many of the tools which you have developed. So this is a simple situation. So we don't need even the completeness. So in the case of separability, we are allowed to consider just inner product spaces. Of course, non-trivial. So the statement is that if we have a separable inner product space, then there exists an orthonormal basis in X. And this basis is at most countable. Okay, so the proof is obvious. So if X is separable, there exists a dense countable set, so a sequence which is dense in X. So working with the sequence using the Gram-Schmidt orthogonalization and normalization, from this sequence we obtain a sequence of orthonormal sequence. And then one can show that this is an orthonormal basis because this family is complete. That is, its closed linear span is actually the whole space. So here, since we have a countable set, so Gram-Schmidt orthogonalization is just as in linear algebra, you start with first point, you normalize it to obtain the vector. So let me write down probably like this. So E1 is just x1 over its norm. So then you consider x2. If x2 is linear dependent with this guy, then you just forget about it and consider x3. So you consider x3 or x4 or etc. So until the first linear independent element. So assume that this is x2, which is linear independent with E1. So you then consider a finite dimensional, two-dimensional subspace. So x1, okay. X1 would be just a span of E1 and X2, assuming that X2 is linear independent with E1. And then here in this finite dimensional subspace, you just make this Gram-Schmidt orthogonalization, that you make orthogonal projection, subtract it, and you obtain something orthogonal, and then you normalize it, and then you get E2, etc., etc. Each time on each step you deal with finite dimensional subset, and everything works perfectly from our knowledge of linear algebra, roughly speaking. Okay, so in this nice special case, everything works perfectly with just standard Gram-Schmidt orthogonalization. So let me write down like this. I hope everything is clear and we don't need to write down too much. So do you know what the Gram-Schmidt orthogonalization is?
Yes, I remember.
Okay, so okay, then everything is totally clear. Okay, are there any questions concerning this? Okay, so let us go further. So please pay attention that if we have a separable in a product space, then it's ONB. So there exists an ONB and its cardinality is countable, at most countable. Now the following theorem, the theorem of Ries and Fischer. So each infinite-dimensional separable Hilbert space over some field K is linearly isometrically isomorphic to the space small L2 over K. So this linearly isometrically isomorphic means that there is a mapping between X and L2 small, which is a linear isometric isomorphism. That is, it is a linear mapping, it is a bijection, and it is an isometry. And proof is very obvious, I would say. So consider. So let me write it down like this. Let X be a separable Hilbert space. And then we know that there exists an orthonormal basis. Then there exists an orthonormal basis. It is at most countable, but since we have infinite dimensional Hilbert space, so it is countable. So it is not finite. So there exists a sequence which is an orthonormal basis of X. Okay, then consider the following mapping. Let it be J. J maps X in L2 in the following way. We take X and map it to the following sequence. Where xn is nothing else but the coordinate of X in this basis. So the Fourier coefficient of X. So we take X, we decompose it, so find its coordinates due to this basis, with respect to this basis, and hence we map X onto the sequence of its coordinates, Fourier coefficients. So then J is linear due to linearity of scalar product. Hopefully it's clear. And by Parseval equality, the norm of X, okay, squared is just, okay, let me write down without squared. So this is just the sum of X n squared 1/2. But this is just, so here we have my Xn. These are my Xn. So what stays here, it is just the norm. Okay. This is the norm of this sequence Xn, norm in L2. Or maybe I should write it in a nicer way. This sequence is nothing else but J of X in L2. Hence, we see that we have the isometry. J is an isometry. Yeah, so it preserves distances between elements. So the distance between x and 0 is the same as the distance of its image and 0, an image of 0. But this is 0 due to linearity of J. So J is isometry. Is it clear?
Yeah.
Yes. Okay, but since J is isometry, it also an injective mapping. So each isometry is injective. Yes, because the distances between elements are preserved.
Yes.
Okay. Moreover, J of the whole X is the whole L2. That is, J is surjective, surjective, because since for any sequence xn elements of since for any element of L2 small, what do we have? We have that. Okay, let me write down. It was exercised last time, but let me write it down now explicitly. What we have used already several times. That we can show that the corresponding sum of x k e k. So this is a Cauchy sequence. So we show it in this way. We see that this is nothing else but this sum. We use just orthogonality. Yeah, everything is finite. We use scalar product, orthogonality, and we have this. And since this is the sequence from L2, so the series of such things converges, and hence such pieces of this series, they tend to 0 when m and n tend to infinity. So the tails, and hence we have shown that this guy, so these partial sums, that this is a Cauchy sequence in X. And hence, since our X is a Hilbert space, there exists some small x in X, which is the limit of this sum. And hence, what we have that J of this small x is exactly this sequence xn. So we have shown that this mapping J is surjective. Since it is also injective, it is a bijection. So we have shown everything. Linearity, bijection, and isometry. Do you have some questions? Okay.
No,
Yeah.
I mean no question.
Okay. So what do we have? So we now understand very well infinite dimensional separable Hilbert spaces. They all are linearly isometrically isomorphic to the space small L2. So we understand them very well. So we understand how to deal with them, how to yeah. So you actually need to find an orthonormal basis. Now you know that such basis exists. You know that it is countable in this infinite dimensional situation. And now you just decompose all elements using this basis. You find their coefficients, so Fourier coefficients in this basis, and then you work just as if you would be in L small 2, L2. So everything is totally perfect then. So the only thing which is not yet discussed is how to find an orthonormal basis. So we now know that it exists, but how to find it is the next question. And once again, this is the situation when we have infinite dimensional separable Hilbert space. So let me first summarize what we have so far. We have the general situation, just a Hilbert space. And we know that if there is an orthonormal system which satisfies one of these four properties, then this is an orthonormal basis. We have proved, okay, very easily that in the case of separable inner product space, not even complete, there exists an orthonormal basis, which is at most countable. What is next? Now it will be like an advanced remark with some further results, which are like not the main material, but still they are good to know that they are so as they are. So first statement, so let X be a Hilbert space, not necessarily separable. Of course, we consider a non-trivial situation. Then there exists a orthonormal basis in X. Now nobody promised that this orthonormal basis will be countable, yeah, or at most countable. This is not the case. This is the general situation. So we're not going to prove it in all details, but I give you the reference. So this is theorem, this number in the book of Bogachev-Smolyanov. So I use the Russian version of this book. But the idea of the proof is as follows. So we consider the set of all possible orthonormal systems. There is a partial order on this set just by inclusion. And then we use the lemma of Zorn to find the maximal element. And we show that this maximal element corresponds to a complete system of vectors, which is then by this characterization, yeah, complete is the same as orthonormal basis. Okay, now my question is, do you know the lemma of Zorn or not? So is it something known or not?
Not that clear. As I remember zone lemma, we should construct a partial order and then consider every chain as
Yes.
a maxima. Okay.
Yes. Yes. Okay, so it's home task for you to read what is it. We will, I guess we will use it in the sequel, but I would prefer not to give much time to this proof and to discussion of lemma of Zorn now at this point. But I guess roughly speaking, it's clear what happens. So there is this set, there is a partial order, each chain possesses a maximal element. And hence, this lemma of Zorn says that there is a maximal element in the whole set. And then we show that this is a complete system and hence an orthonormal basis. Okay, so please remember that in the case we have a Hilbert space, there is an orthonormal basis. Also, in the case when we have a separable, but probably not complete space, not Hilbert space, just inner product space, but separable. We have also proved that there is an orthonormal basis. Yeah. Now, next remark. Wait. Okay. First example. So I have claimed that for any Hilbert space, there is an orthonormal basis, even in the case when the space is not separable. First of all, example. So as I said, in the case of separable space, Hilbert space, it is a linearly symmetrically isomorphic to small L2. Now, let us make a more advanced version of L2, namely, so let omega be uncountable. And as L2 of omega, we consider the set of all mappings from omega to okay, let it be R, okay, field of our scalars. So all mappings such that at most countably many values are non-zero. And then the mapping such that this sum contains at most countably many summands due to this, such that this sum is finite. Okay, so ordinary L2 is just L2 over natural numbers. So it's a countable set. Now instead of natural numbers, we consider just some uncountable set omega, but do all the same. So we organize L2. Then the inner product looks as follows, as an ordinary L2, but now we have a sum over all small omega from big omega. But remember, since this holds, so this sum also has at most countably many summands. So it is well defined. So then one has to prove that this set is a Hilbert space. That is, linearity is hopefully clear. So it's a vector space. Scalar product is given. And then completeness, this is what one has to show. And then the standard orthonormal basis is just the indicator of omega. So in this standard case, this would be just this basis of 1, 0, 0, 0, then 0, 1, yeah, etc. But this is just, all of them are just indicators of, okay, I don't know how to say, yeah, case EK, so this is E1, E2, and EK is just indicator of a case position, so to say. In the same way here. Okay, I hope it's clear how it is all organized. So it's a generalization of standard L2. And this is a kind of standard example of uncountable Hilbert space and not a normal basis there. Okay, so let us go further. So as I stressed once again, so if we have a Hilbert space that is a complete space, we have a not normal basis. Moreover, we have proved already that if we have a separable inner product space, no completeness, but separability, we again have orthonormal basis. Now, next statement, there exists a non-separable and incomplete inner product space which does not possess an orthonormal basis. So you need either separability or completeness to get a basis. If you don't have both of them, you may have problems with orthonormal bases. Yeah, so there is a counterexample. You can find it in the book. Okay, so let us go further. So once again, this remark is just a series of further remarks, so to say. Not the basic material, but some further remarks. Okay, number 3. An orthonormal basis in a separable Hilbert space is a special case of a Schauder or so-called topological basis of a topological vector space. So I give the simple version of this definition of this Schauder or topological basis. So now we have a norm space. A sequence En in X is called a Schauder basis for X if for every X there exists a unique sequence of scalars from our field such that X is the sum of this series, where the series converges with respect to the norm. That is a norm of X minus some k from 1 till n. Ck, ek, the norm of this stuff converges to 0 when n tends to infinity. So, so if you compare this statement with the definition of orthonormal basis in a Hilbert space or in an inner product space, you see that the requirement is the same. That we can represent each X as such a sum. Please pay attention that so of course, so Schauder basis is a generalization of an orthonormal basis in the separable Hilbert space. But as soon as we start to generalize something, we have to accept that the properties of this generalization will be not as fine as the properties of the original object. So this is what happens here. So it's nice to have a kind of basis in even a norm space, not only so even if you don't have an inner product space, but so if we have a family of vectors in X such that this family is linear independent and such that its linear span is dense, so I would say like system is complete. From this, it does not follow that the system is a Schauder basis in X. So so you see in Hilbert space this is not possible, but in a norm space there is such a problem. So complete system does not imply that it is a Schauder basis. Further, a Banach space with Schauder basis is necessarily separable, well, looking from the definition. But not all separable Banach spaces possess a Schauder basis. So this is also a property which is worse than in the situation of Hilbert spaces. So not all separable Banach spaces possess a Schauder basis. As a positive, so hello, do you still hear me?
Yes.
Yes, but I see that that my slides somehow do not change. So I change them on my iPad, but it is not changed. You see page 23 still, yes?
Yes. The slide and change.
Okay, so then okay. So it's something strange. So let me. So something is going on. Yeah, so there is a problem with my Zoom probably.
I think restart screen share will help.
So let me. Okay, so now you see, and I see that you see. Okay, so this is what you didn't see, what I have written. So this is what means that this series converges to X in knowing. So as I said, so Schauder bases have not as nice, their properties are not as nice as the properties of orthonormal bases in Hilbert spaces. So one remark is that if we have a family of vectors which is linear independent and with a dense linear span, this does not guarantee that this family is really a Schauder basis. This is one remark. And another remark, so a Banach space with Schauder basis defined like this should be necessarily separable, but not all separable Banach spaces possess a Schauder basis. And more, as a something positive, so for some nice Banach spaces like LP or continuous functions on a segment, there are Schauder bases, they are found. So in this case, it is a base of Haar functions. And in this case, this is a base of Faber-Schauder function. So it's a home task for you to clarify what they are, these functions. Now I can just try to show you a picture. Yeah, so this is how Haar functions look like. Okay. And if you integrate them, you obtain Schauder. I don't know how to close this. Okay. Haar functions and Schauder functions. Okay, so this is an important function. So Haar functions also for the so-called wavelet analysis. Okay. So what I wanted to say is that the idea of orthonormal basis can be generalized also for normed spaces. Then we obtain something which is called Schauder basis. And the properties are worse than those of ONB in Hilbert space. But nevertheless, for some good spaces, there are known Schauder bases. That is, we can do approximations. That is, we can approximate any element from here or from here by the corresponding partial sums of series in these Schauder bases. So this is a positive result. Also, a small remark that, so when I defined an orthonormal basis in a Hilbert space, it was not necessarily a countable sequence. Yeah, sequence. It was a family of E lambda, and we don't know how big was this E lambda. But then the requirement was that for every x, there exists a subsequence, so a subfamily of this family, which is countable, at most countable, so that every x can be approximated by such sum with at most countably many summands. So using at most countably many elements of this big family. Of course, in this way, I can also generalize the notion of Schauder basis, but there is one smallness which make it not as fine as in this case. And this smallness will be discussed in item 4. So item 4, a Schauder basis En is called unconditional if it remains to be a basis after any permutation of its elements. So here, so we have this identity. We change the order of summands. So take any permutation of natural numbers and consider the sum after permutation. So the requirement is that the sum after permutation should also converge and to the same x. This is what means that the basis is unconditional. So the good thing is that in the case of Hilbert spaces, even without the word separable, any orthonormal basis in a Hilbert space is unconditional. But if we consider Schauder's basis in the more general situation, in the norm space, this is not the case. So not necessarily happens. That is, for example, in this case, in this space, there is no unconditional Schauder basis. So there appear some problems with this big family and such that each x has a most countable subfamily such that this holds. So it is nice and convenient to work in Hilbert spaces because we really don't care about the order here in this sum. But in more general situation, the case of Schauder basis, we should really take care about the ordering of elements in the basis or in the sum. Okay, and this is a book in Russian where you can find some information about this statement. Okay. Are there any questions concerning Schauder bases?
I think it's hard to imagine how permutation can make a basis be not a basis.
Well, actually, it is not that hard to imagine because even if we are, if so, let me formulate like this. So even if we are in the case of real numbers, yes, and we consider just a series of some elements, ck. So we know that it is not always so that if so that this sum converges unconditionally. Yeah, this all only happens if all ck's are positive. So if we have that this converges, then this sum converges unconditionally. That is, if we make a permutation of the order, so if we make a permutation of summands, then the sum still converges. Yeah. So since it is not a finite sum, it's an infinite sum of we have infinitely many summands. So there is this conditional unconditional convergence. It is discussed in mathematical analysis, I guess, first semester. So do you remember something like this?
Yeah.
Yeah, so this is a kind of what we discuss here. It is actually a kind of generalization. That is, so one can show that in any normed space, if we have a sequence xn elements of x is a normed space, such that the sum of norms converges, then we can claim that this sum converges. It converges. But this is okay. Wait a minute. Okay, so let us come back to the case of real numbers. Numbers. So this is the absolute convergence. So this series converges absolutely if this holds. And we say that this series converges unconditionally if we make any permutation of summands and the sum converges anyway. So in this case, these two things are equivalent. So unconditional convergence is if and only if absolute convergence. But this is not the case in normed space. So what I have written here, this is absolute convergence, so to say. So if we have a sequence of elements which converges absolutely, roughly speaking, then it converges. But it doesn't. But unconditionally means that this series converges after any permutation of summands, and this is not. So probably I have something. I don't know. What do you see now? You see my slides? Yes, I guess you see my slides. Okay, so there is the so-called theorem of Dvoretsky-Rogers, which says that a counter example, which says that if we have a sequence xn in a normed space, even in a Banach space, such that okay, the norm xn is equal to 1 over n, there exists a sequence with such norms, such that it does not converge absolutely, because yes, harmonic series does not converge. So there exists a sequence such that it does not converge absolutely, but it converges unconditionally. Xn converges unconditionally. So actually, I didn't plan to discuss it, so there are a lot of fine things which appear as soon as you want to generalize standard things. So what is nice in Hilbert spaces, that everything runs as one should expect having linear algebra. That is, in a Hilbert space, any permutation of vectors in the basis, and hence the corresponding permutation of coordinates of all other vectors in this basis, they do not break anything. That is, after permutation of elements of ONB, we still have ONB, and that is each x which is can be approximated by elements of both ONBs. And by definition, the Fourier coefficients of a vector in one ONB is obtained by the corresponding permutation of its Fourier coefficients in the original ONB. So everything works perfectly as it would be in finite dimensional space. In the case of norm spaces, we lose this unconditional convergence. So we should really take care about the order of elements in the basis. And also, yeah, you see how the convergence of norms is related to conditional and unconditional. So actually, there is another theorem which says that okay, I think we should not go deep in this direction. It's a home task for you, if you are interested in to clarify what is O means. I give you this name, Dvoretsky, Rogers theorem, on counterexample, and I guess let me look in the Wikipedia. I guess there is this article in Russian and in German, but not in English. But probably you can take German and use DeepSeek to translate into English or to any other language. Okay.
Okay.
So just the message from this remark. The notion of basis is very important. This is a nice notion in order to approximate elements of some infinite dimensional normed space by such partial sums using the elements of basis. But everything fits perfectly to the intuitive things in the case of a separable Hilbert space, or even without separable, just in a Hilbert space. As soon as if you work just in a norm space, you should be careful, in particular, take into account this. Okay, let us go further. One more remark, number 5. This is about our dimension. We have, so I specified many times, so I have used these words many times. Infinite dimensional separable Hilbert space. But what does mean infinite dimensional? So we have not clarified in which sense we understand the word dimension. Okay, so if we have not clarified it was a Hamel dimension, okay? So by saying this, I mean Hamel dimension. And now we are ready to discuss different notions, so Hilbert dimension or orthogonal dimension. So Hilbert dimension of a Hilbert space is the cardinality of its orthonormal basis. So my question to you, if we have a separable Hilbert space, what is its Hilbert dimension? So question, what is the Hilbert dimension of a separable Hilbert space?
Countable or less?
Yes, countable. Yeah, cardinality, so the set of vectors in ONB is a countable set, so dimension is the same as dimension, so this continuum. Sorry, so not continuum, sorry. Countable. Okay, and also all ONBs in X have the same cardinality. Well, this is somehow follows from the theorem which we have, well, which we mentioned but did not prove. So this one, and due to construction, it somehow follows that all ONBs have the same cardinality. Okay, so Hilbert dimension of X is not greater than its Hamel dimension, and Hamel dimension of any infinite dimensional Hilbert space is uncountable. So even if we are in small L2, in a separable Hilbert space, a Hamel dimension is uncountable. This follows from the theorem of Baer about categories, but we have not discussed this theorem because we have not discussed the theory of metric spaces, assuming that you already know it. Or, okay, just believe that this is so. Okay, so I guess I have clarified everything. So as a summary, it's very nice to work in separable Hilbert spaces. We know that there exists an orthonormal basis, which is at most countable. So in infinite dimensional space, it is countable. We know that it exists. We know that it possesses nice properties. Like completeness of the system, closeness, totality. And now the question is how to construct, how to get these ONBs. So we know that they exist, perfect, but how to get them? So now we have just a very few time, but I wanted to present you some basic examples. For example, 333 ONBs in Hilbert spaces. So how to get them? For example, one way is to use Gram-Schmidt orthogonalization of a nice. So as we did, if we are in a separable Hilbert space, we just take a set which is known to be dense and make Gram-Schmidt orthogonalization. So this is what we do first. So we consider mu a measure on a Borel sigma algebra on some interval, so finite Borel measure. So then this is a result of mathematical analysis, so to say, that the set of all polynomials is dense in this space. So you can consult Kolmogorov-Fomin, the book of Kolmogorov-Fomin, to get this statement. And so since all polynomials are dense here, so we take a linear independent subsystem of all polynomials, and using Gram-Schmidt orthogonalization of this subsystem, we obtain an orthonormal basis. That is a system which is complete here. And hence, it is an orthonormal basis. Okay, so it's clear how to proceed.
Yes.
Yes, perfect. So some special cases. So special case number A. So we consider this interval from -1 to 1 as a measure. We take Lebesgue measure. So then we use Gram-Schmidt orthogonalization of this system of monomials. And what we obtain as a result, they are the so-called Legendre polynomials. They look like this. So L0 is just constant, L1 is just x, L2 is a polynomial of second order, etc. Then Ln is a polynomial of order n, and it is given by this nice formula. This is the so-called Rodriguez formula. Yeah, so since this is a system which is obtained from from this guy by orthogonalization. This is an orthonormalization, better to say. So what we obtain is actually an orthonormal basis in this space. I guess there is a picture of such polynomials, so constant x, and then all other polynomials. All pictures, this one and the subsequent pictures, they are taken from Wikipedia. Okay, so this is one example. Second example, B, or not, first of all, one remark. So this function ln solves the following ordinary differential equation on this segment. You may just insert this formula and check that this identity holds. But what does mean this identity? So we can take this guy and go put it here on the right-hand side. And the left-hand side we can rewrite in the following way. So actually this identity is the same as this identity. So these two summands of the sign minus give us this. But this means that this vector L, which is a solution of this equation, is just an eigenvector of this operator with eigenvalue n times n plus 1. Please remember it, because actually the typical situation how to get an ONB in some Hilbert space is just exactly like this. They are a class of operators which are so nice that their eigenvalue, that their eigenvectors form an ONB. So the way how to get an ONB is just to take an operator, check that it belongs to a particular class, and then we know that its eigenvectors is just ONB. Okay, so we have this. Now, example B. Now we consider the same segment, but another measure. Mu is the so-called, so this measure, so with some weight. Not Lebesgue measure, but a measure with a weight. Then we do the same procedure, the Gram-Schmidt orthogonalization of this stuff and also normalization. And what we obtain is the so-called Chebyshev polynomials. So this is the general formula. Cosinus of n are cosinus. But after application, you see that T0 is 1, T1 is x, T2 is the polynomial of second order, of second degree. And yeah, so this guy will be a polynomial, again, a polynomial of nth degree. Yeah, and the system of Chebyshev polynomials is an ONB in this space. And again, a picture from Wikipedia, how they look like. Again, this is the first polynomial, this is the second polynomial, and then more advanced. Okay, and again a remark that Chebyshev polynomial solve the Chebyshev differential equation. It looks as follows on this segment. Again, this means that the solution of this equation Tn is just an eigenvalue of this operator with eigenvector of this operator with eigenvalue n squared. So this is the operator with minus and then this with plus. Okay, so as a key word here, I would say Sturm-Liouville operator. But what is it? It is too early to discuss. But just remember that ONBs are very nice and helpful. They allow to approximate things in infinite-dimensional spaces. And they are closely related to a special class of operators. Okay, we go further. Now we have this space, so not a segment, but the whole R. And we have a mu measure, which is just a standard Gaussian distribution. So then this is the result which one has to prove that all polynomials are dense in this space L2 with this Gaussian measure. And hence we again are allowed to make Gram-Schmidt orthogonalization and normalization of this set of monomials. And what we obtain as a result of this activity, we obtain the famous Hermite polynomials. This is the formula for Hermite polynomials. So you take Gaussian exponent, you differentiate it, and then you obtain a polynomial times exponent, and you kill exponent by the exponent with opposite sign, so with plus, here minus. And what you obtain finally, it is a polynomial. Again, a picture from Wikipedia, how these polynomials look like on R, but with Gaussian measure. There is a dual picture of this. So the statement that Hermite polynomials is an ONB here is equivalent to the statement that Hermite functions. So you have this compensation. So Hermite polynomials times this compensator, so to say, they are an ONB in L2 with Lebesgue measure. So either you need weight to the either you add this weight to the measure, or you add this compensator to polynomials to have functions which decay in L2 with Lebesgue measure. But you can see you can see what is inner product here and what is inner product here, and you how to say, you pass from one ONB to another ONB, but just considering scalar products in the corresponding spaces. Okay, we go further. It's just for, how to say, Alice, this is pudding, pudding, this is Alice. I guess that you know all these, at least names of these functions. So I just wanted to stress that many well-known functions are nothing else but just orthonormal bases in Hilbert spaces. And they are also related to some operators. And again, so remark, so the Hermite polynomials solve the following equation. That is, again, Hermite polynomials are eigenvectors of this differential operator, yeah, with the corresponding eigenvalue. So in all these examples, we have second-order differential operators. B, case B, we now in the half line, and now measure mu is this exponential distribution. So again, this is the result to prove that polynomials are dense in this set, in this space. And hence we can proceed with Gram-Schmidt orthogonalization. So if we orthogonalize the monomials, we obtain the so-called Laguerre polynomials. And this is again the general formula. All formulas of this type, they are Rodriguez formulas. Yeah, this is a picture how this, so we start from zero. So actually we are interested in everything what is here. But again, so this is the way to obtain an orthonormal basis in this space. And again, we have, so this is not a bounded segment, as also in the case A, but we have the weight. So either we consider polynomials and have the weight in the measure, or we consider Lebesgue measure, and then instead of polynomials, we create functions, the so-called Laguerre functions in this case, where instead of this weight, we put compensators to our polynomials. And again, if you consider scalar inner product of Laguerre polynomials here, it will be the same as inner product of these Laguerre functions here. You just play with these exponents where they stay. Okay, and again, remark Laguerre polynomial solve the following differential equation here on this interval. And this means again that Laguerre polynomials are eigenvectors of this differential operator with the corresponding eigenvalue. Okay. Now trigonometric system. So now I see that we have no time anymore. But I guess that trigonometric systems is something known for you from the course of analysis 1 or 2, where the Fourier series, so classical Fourier analysis Fourier series were discussed. So is it so or not?
At least I know the existence of a trigonometric system.
Okay. So let me say a few words here again. So before what we did, we have some results saying that polynomials are dense in the space we are interested in, and we did Gram-Schmidt orthogonalization of polynomials. So this is one way to construct an ONB in many different situations. But here we have something else. So we have a segment, and the claim is that so this system is an orthonormal basis. And this system corresponds to what is known as Fourier series. That is, the Fourier coefficients of any element from this space with respect to this basis are the classical Fourier coefficients of this vector. And yes, this is a special result which shows that this system is complete. That is, we really have not only an orthogonal system, but an orthogonal basis. Now, this is not an orthonormal basis. In order to normalize it, we need to divide with some constants. I guess it should be like something like this here, and here some other like this to make orthonormal basis. But we can survive without normality. So just orthogonal basis. Yeah. So there is a non-trivial result that yes, that this system is complete in this space. So I refer to the book of Kolmogorov-Fomin, so Russian edition, so where you can find how it is proved. Okay, but now, so it's another way. So it's not a Gram-Schmidt orthogonalization of polynomials, it is something else, so from separate result. And having this basis in this interval, one can create some further basis. In particular, if one considers so an interval which is twice less than this one, so only half of this interval, then one can split this system into two parts. One part is only with cosines, and another part is only with sines, sinus, only sinuses here and only cosines here. One is just cosine with n equal to 0. So both systems are orthonormal bases in this smaller space, so to say, space on the smaller interval. So how to show this? We just take any element, so any element from this space. So it's a function defined here. We can extend this function to this bigger segment so that this extension is like even function or odd function. And depending on how we extend, if we extend to an even function, so we extend it to here. Here we have a basis. We decompose the element, so we find its coefficients in this basis, and it turns out that due to the fact that the function is even, only coefficients at cosines survive, and coefficients at sines will be 0. So what we have, we take any element from here, extend it to an even function here, decompose it here, and obtain that actually decomposition is decomposition using only this system. In a similar way, if we start from here, take any element from here, extend it to an odd function on the segment minus pp. So we start here, go here, have an odd function here, decompose it using this system of using this ONB, and it turns out that in this decomposition only Fourier coefficients at sine functions survive, and all the rest are 0. Hence, each function from here can be represented as a series using only sines. So both systems are ONBs in the same space. Okay. A remark. So this function, so from this ONB, including n equal to 0, this is this case. So these functions solve the following boundary value problem. So these functions are eigenvalues of Laplacian and with Neumann boundary value conditions. And elements from this system, sine functions, they also eigenvalues of the Laplacian with the same n squared, but with another boundary conditions. So this is the Dirichlet boundary value conditions. So you see Laplacian with different boundary conditions, they are different operators and they have different eigenfunctions, eigenvectors. And again, even this trigonometric story, they are also related to eigenvalues of some eigenvalues and eigenfunctions of some differential operators. Okay, and one more basis from trigonometric. So this all was over R. Now, if we want to have over C, the following system is an ONB in X. Again, how to show it? If we have an element from here, then its real part and imaginary part are elements from here. Then they can be decomposed using this basis, and then using Euler formula, which which represent such exponents via sine and cosine functions, we come back here. Okay, I have not written anything, but I hope that it's clear for you what happens. Okay, seemingly this is not the case. Yes. So now my question. Do you want some more detailed exposition or it's enough to have what you already heard?
A more explanation for what?
For the trigonometric systems that they are ONBs. So I try to explain how we get this ONB starting from here and how we get this ONB starting from here. So was it clear or not? Should I write something?
When I learned this part, as I remember, I think the Waterstein-Stone theorem can just solve the proof, right? Oh,
So okay, this is about the statement that ONB is that trigonometric system is ONB in X. Yes, one of the ways Stone-Weierstrass theorem, which shows that polynomials are dense in continuous functions, and then continuous functions are dense here, and polynomials on a proper interval, they can be organized in a way that they are actually sine and cosine, or if we oversee these functions. Yes.
maybe what you said is Waterstein theorem. The Stone generalized this theorem that if you have a compact set, then if for example, the set of polynomials satisfying three properties, I'm not sure. For example, not one-ish and something. Then it's the linear span propose the whole space
Of continuous functions. Yeah, polynomials
okay.
are dense in continuous functions. So then one should prove that continuous functions are dense here. And yes, and since we have this interval, there is an interplay between polynomials and such functions. You just use the parametrization to have such functions instead of polynomials.
Yes.
Yes. So you are right. This is one of the way to prove that we have ONBs here or here. Okay, so one more thing which I wanted to say, I guess Yeah, so part D, so by linear transformations, one obtains trigonometric orthogonal basis in the space of this way, of the space L2 over a segment AB over a real or complex number. So if we consider this case, we can organize 3 different orthogonal bases on this space, like this, or like this. Sorry, like this, or like this, but by proper linear transformation of variables, of course. That is generally on such space over C, where we have 3 different orthogonal bases. Orthogonal bases only from sine functions, or only from cosine functions, or from both. For this aim, we need to scale. So we make a linear transformation of variables such that this interval of this interval is mapped to this interval. Again, I do not write any formula. I guess this is not so important, but if one needs, one can write down it himself. So the last thing for today, it is a kind of an extra thing. So why all this topic is also very interesting for people who deal with stochastics. So Brownian motion can be represented as a random orthogonal series. So it is done as follows. So we consider the space L2, interval from 0 to 1 with Lebesgue measure. So this is the inner product in this space L2. So we take any orthonormal basis in this space. Since we know that continuous functions are dense in this space and polynomials are dense in the space of continuous functions on this segment, we know that this is a separable Hilbert space. Polynomials with rational coefficients, they are this dense countable subset of this space. So we know that there is an ONB in this space, and this ONB is countable. Okay, so we take an ONB in this space, and we take a sequence of real valued IID Gaussian, standard Gaussian random variables on some probability space, omega FP, and we consider such random variables. So it's some from n to some big N, IID Gaussian, standard normal distribution, standard random variables with standard normal distribution. And here we have a scalar product, basis vector, and this function, which of course belongs to this space. The statement is that this limit exists in this space for each point t. I'm sorry. So this limit, so for each fixed t, we have a random variable from this space. So finally, we have a process. And actually, the statement is that this process is a Brownian motion. That is, even the paths are continuous. So this is the book where you can read more information about this. But this is one of the way to construct Brownian motion. Special, I have not yet finished, so let me finish and then you ask your questions, okay?
Yes.
Sorry. If we take a particular orthogonal basis, so we take orthonormal basis, which we obtain by normalization of this basis. And then our Brownian motion looks as follows. So this is the limit of such things for the particular choice of the basis. And this is actually the classical construction of the Wiener himself. So it's like in this year. So this is a Brownian motion. There is also the so-called Levi-Chiselsky construction. So the same construction, but one uses not the trigonometrical basis, but the basis of Haar functions. And some similar things one can do not only with Brownian motion, but some for for a class of processes. And this is then called Karunen-Loew expansion. So this is a keyword. I do not say anything more, but you know the keyword. You can learn yourself more about all this story. And now you are welcome to ask questions. I guess there was a question.
Sorry, I have already understand that it was stupid question. Sorry.
Okay. Don't be afraid of asking stupid questions. If you ask questions, you get answers. If you don't ask questions, you don't get the answer. Okay. So we have finished the topic inner product spaces, normals, normed spaces, orthogonal projections, orthonormal bases. So the message is as follows. So if we are in the Hilbert space, in particular in inseparable Hilbert space, then everything runs perfectly as we could expect, knowing linear algebra, roughly speaking. And this is very helpful in many situations, also in stochastics. Nevertheless, one can generalize all the story, even for the case of normed spaces, and then in some spaces there are nice bases, Schauder bases, where something good still happens. And you're welcome to learn yourself further about the applications. Okay, so next time we will start next chapter about linear operators. Now I stop the recording.